Good morning and welcome back to Math 098. Good morning, Ashanti. So we talked last class about exponent rules. We started, good morning, Moana and Johanna. Perfect, thank you for joining us. Last class we talked about the product rule and we started to dissect the quotient rule. So recall with the product rule, you're going to keep the base, add the powers, right? So if your bases are both x, you keep the x, and then you simply take those powers and you add them. You can have numerical bases as well. So let's say your base were a 6, right? So you have 6 to the 3rd times 6 to the 11th. Well, that's going to be 6 to the 14th, right? You keep the base, you add the powers. Remember that. Just keep saying that. Keep the base, add the powers. Now, when we talked about the quotient rule, that was a little bit interesting, right? Because we essentially looked at those common bases. We kept the base, but we subtracted the powers. Now, when we subtracted the powers, we left it where it was heaviest. So, for instance, if you had x to the 2nd power over x to the 5th power, well, you're going to be left with x to the 3rd in the denominator. Yes, of course, Kevin, no worries. So you're going to be left with x to the 3rd power in the denominator because you're subtracting them. You're essentially saying, if I have 2 x's in the numerator but 5 x's in the denominator and I take away the 2, then I'm left with 3 in the denominator, right? That's kind of how we think about it. This way we avoid negative exponents. When we have negative exponents, we actually have to use a specific rule, which hopefully we might actually get to today. So we're going to continue with the exponent rules and let's look at the power rule at this point. Check it out. So we have something called the extended power rule. It's essentially the power rule, but I wanted to show you what it looks like in its full glory. So if you have x to the m times y to the nth power, and you're raising this entire expression to the 8th power, well, all you have to do is distribute a times m, a times n. So notice it's x to the m times a, and then y to the n times a. Think about it as I had to distribute that power to the other powers, right? So you keep the base, but you multiply power by power, all right? And that power is on the outside of the set of parentheses. Think of it like distributing the power to the other powers. Never multiply the power by the base. That doesn't make sense. You would never multiply a times x. X is a base, a is a power. N is a power, so why not multiply power times power? Keep that in mind. Now, notice the second expression. What if you had x to the m over y to the n and all of this raised to the a power? Well, you're still going to do the same thing. You're still going to distribute power times power. So it becomes x to the m times a power over y to the n times a power. For clarity, let's check out the differences between these two expressions. Notice this first one, we have 7 to the 2nd power times 7 to the 3rd. Well, according to what we see here, we note that this is the product rule. According to the product rule, we're going to keep the base, add the powers. Done. 7 to the 2nd times 7 to the 3rd is, in fact, 7 to the 5th power. For our next example, we have 7 to the 2nd power raised to the 3rd. Now, check this out. Because we have 7 squared raised to the 3rd, that's the same as saying, well, take this 7 squared and multiply it by itself 3 times. Doesn't that say that? You have 3 of these, and you're going to combine those. 7 squared times 7 squared times 7 squared is 7 to the 6th power. Keep the base, add the powers. If you don't believe me, well, that's not a big deal. I can simply show you with the calculator. So 7 squared times 7 to the 3rd power is going to give us 16,807. You see it? So now I'm going to do 7 to the 5th power. 7 to the 5th power, and voila, 16,807. It's exactly the same. Now, we want to note that 7 squared to the 3rd is the same as 7 to the 6th power. So let's use parentheses. 7 squared to the 3rd power gives us 117,649. And now I'm going to punch in 7 to the 6th power. And we get the exact same answer, 117,649. I highly recommend that as you do these, as you work with the numerical basis, just do a quick check to make sure that you're getting this correctly. Now, let's take a look at the power rule. We have 4m to the 5th, n to the 12th, all raised to the 3rd power. Recall how many bases you have. Good morning, Maria. No worries. You have a base of 4, a base of m, a base of n. The powers of each are as follows. This 4 is being raised to the 1st power, right? Because we don't see that 1. So we're going to actually write that in. And you know, let me get a little bit closer here. So we have 4 to the 1st power, m to the 5th power, n to the 12th power. We are raising this entire expression to the 3rd power. So you're going to take that power of 3 and you're going to distribute to the other powers. Keep the base, multiply the powers. 1 times 3, 3. Keep the base, multiply the powers. 5 times 3, 15. Keep the base, multiply the powers. 12 times 3, 36. Now, typically, we would look at this and say, well, I can do 4 to the 3rd. If I took my calculator and I punched in 4 to the 3rd, it gives me 64. So what I'm going to do is I'm actually going to simplify that as well. So my answer should be 64, m to the 15th, n to the 36. And that is how we want to record our answer. If for whatever reason we did the math, and let's say that was 4 to the 12th power, well, if we typed in 4 to the 12th power, look at how crazy that value is, right? So in which case, I would actually ask you to leave it in exponential form. Leaving it 4 to the 12th would be better than writing that whole thing out. But again, that takes practice, and you'll notice what you're expected to do, whether you're expected to leave it in exponential form or if you're expected to evaluate that. Cool. Let's turn the page. Let's do some more. For number 2, we have negative 3x to the 11th y, all raised to the 4th power. So we're going to break this up piecemeal. First thing, we have a base of 3, a base of x, a base of y. We also have a negative value. We'll deal with that in a second. This base of 3 has a power of 1. Make sure you write it in. The base of 11 has a power, the base of x has a power of 11, and the base y has a power of 1. Okay. Now you're going to take your power on the outside, which is 4, and you're going to apply the power rule, which states distribute power times power. So that gives us 3 to the 1 times 4, which is 4, right? You keep the base, multiply the powers. X to the 11 times 4, which is 44. And y to the 1 times 4, which is 4. Now you're probably wondering, what happened to that negative? Well, I want you to think of this logically. If I took a negative expression, right, the negative's inside, if I took this negative expression and raised it to the 4th power, would that be a positive or a negative? Let's think about that for a second. So let's think about the idea of what if you have negative 1 and you raise it to the 4th power? Well, that's the same as a negative 1 times a negative 1 times a negative 1 times a negative 1, right? Every pair of negatives becomes a positive. So this becomes a positive 1. These two together become a positive 1. And then 1 times 1 is positive 1. So our answer is actually going to stay positive. It is not going to be negative. Yes, exactly, Kayla. So think about, Kayla's pointing out the fact that as long as you have a pair of negatives, that becomes a positive. But if you had an extra negative, then it would be a negative value, okay? Now, we're not totally done. We can still evaluate 3 to the 4th. So if you punched in 3 to the 4th into your calculator, you're going to get 81 x to the 44th y to the 4th power. Okay, so I have that note here. What I'd like you all to do is to take a moment and first think about this carefully. I would like you to apply the order of operations first. So I'm actually going to indicate the order in which I'd like you to apply your rules. So the first thing I'd like you to do is I'd like you to apply the quotient rule for number 3. After you apply the quotient rule for number 3, then I want you to apply the power rule. I just want to give you a couple minutes. Just take 2 minutes, play around with this, see how it goes. Remember, apply the quotient rule first, then apply the power rule. 2 minutes starting now. So if we were applying the quotient rule, the first thing I would suggest is I would say, well, I have a 6 and I have a 54. The 6 is in my numerator, the 54 is in the denominator. Think about it like this. If you had the fraction 6 over 54, wouldn't you reduce it? If you're all saying yes, then that is awesome. If you are going to reduce it, you're going to say, okay, well, I can actually divide a 6 out of both. If I divide a 6 out of both, I'm left with 1 over 9. So notice the first thing I'm going to do is I'm actually going to simplify that fraction 6 over 54. That leaves me with a 1 in the numerator and a 9 in the denominator. Next, I'm going to look at the base b. I have 12 b's in the numerator, but only 3 b's in the denominator. So when I take them away, thank you, Kayla, for sharing your work. When I take those away, I'm going to be left with 9 b's in the numerator. So this is b to the 9th power, right? Because 12 minus 3 is 9. And then notice you have 1 c in the numerator, but 9 c's in the denominator. So if you have 1 up top, but 9 in the denominator, you're going to be left with 8 in the denominator. Okay, now here's when I say, okay, quotient rule, check. The next thing I'm going to do is I'm going to take this entire expression and note that it's being raised to the 10th power. I'm also going to note that there's a negative in front of our set of parentheses. We recall that when we have a power on the outside of the set of parentheses, and that's okay, Kayla, no big deal. We're doing this baby steps. When we have that power on the outside of the set of parentheses, we're going to distribute power times power. Now, let's refresh our memories. This 1 is being raised to the first power, so we are in the habit of writing those 1's in. Our base b is being raised to the 9th power. Our base 9 is being raised to the first power. And our base c is being raised to the 8th power. So now, take your exponent, your power of 10, and distribute power times power. I find that drawing the lines of distribution help because it's a reminder, oh yes, I'm applying the power rule here. So this gives me negative, right? Because there's a negative in front, so we leave it. If the negative were inside the set of parentheses and we were raising that to the 10th power, well, then that means it's an even number, which means it would be a positive. But because the negative is in front of the entire fraction, it stays there, right? Think about the fact that you're just essentially going to bring the negative with this result. So we have 1 to the 10th power, b to the 9 times 10, which is 90, 9 to the 1 times 10, which is 10, and c to the 8 times 10, which is 80. Now, we know 1 to the 10th is going to stay 1. And I'll prove that to you. So if you have 1 to the 10th power, that's going to give you 1, because it's 1 times 1 times 1, etc., 10 times. So we have our final answer as negative 1 b to the 90th over 9 to the 10th, c to the 80th. I'm going to leave 9 to the 10th in exponential form, because when I take it and punch it in, I get that crazy number. That's super nuts, okay? Just leave it in exponential form. In this case, that would be your final answer. Notice your answer is negative, okay? We keep the negative because it's in front of the set of parentheses. That power of 10 is not being applied to that negative. All right? As always, if you have questions, don't hesitate to ask in the chat. But thank you, Kayla and Claire, for showcasing some of your work. okay? So we're going to be super careful with how we express this. Very nice. Very, very nice. And remember, power times power, not power plus power. Cool. Next, we have something called the zero exponent rule. This one I love because basically any base raised to the 0th power is 1, with the exception of 0. So let's say if you had base x raised to the 0th power, it's a 1, right? Okay, no big deal. I want you to note, though, that g to the 0th power is not the same as g to the 1st power. What I've seen students do in the past is they'll see something like g to the 0 and they'll say, oh, well, that's a 1, so then they write it as g to the 1st power. And I'm like, wait. You just said g to the 0 is 1, which means g goes away. G to the 0 is simply 1, right? It's not g to the 1. That doesn't make sense. They can't be the same. Think about it. They cannot be the same. If g to the 0 is the same as g to the 1, then what's the point? Right? What is the point of having this rule if they're the exact same value? It doesn't even make sense. So think about this carefully. Let me show you a bunch of examples. So our first one, d to the 0th power. Well, your base is being raised to the 0th power, so that's equal to 1. Easy peasy. -5 to the 0th power. That entire quantity, -5, is being raised to the 0th power. So that's going to be 1. 2 to the 0th power. This time we have a numerical base. Who cares? 2 to the 0th power, it's still 1. If you're ever wondering why the heck that is, think of a counting problem. So for instance, let's say that I have this pen here and I'm holding it up and I say to you, in how many ways can you not grab this pen from me? And you would say, 1 way, by not doing it at all. Does that make sense? It's a counting problem. So in how many ways can you not grab this pen from me? And you would say, well, 1 way, by not doing it at all. It doesn't matter how you don't do it, right? You could do a little jig and walk backwards and be like, see ya. Right? Like, it doesn't matter how you do it. The fact is, there's still just 1 way to not grab the pen, and that's by not doing it at all. Okay, let's go back. Next, we have m times d to the n. We have 2 bases. My first base is m, it has a power of 1. My second base is d, it has a power of 0. We know that d to the 0 is simply 1, so this becomes m to the first times 1, which is just m to the first, right? Next, we have -49 to the 0th power. Keep in mind that you do not have parentheses in this expression, so that 0 is only being applied to that 49. 49 to the 0th power is 1, but we still have a negative, so we're going to bring that right over. For part F, we have 5 to the 0th power. We have m to the 3rd, and we have n to the 0th power. Well, 5 to the 0th power is 1, m to the 3rd stays m to the 3rd, and n to the 0 is also 1. So think of it as 1 times m to the 3rd times 1. Well, that's the same as m to the 3rd. And then you're done. Okay, so what we're going to do is we are going to combine rules for these examples. So take a look at this problem number 1. It says simplify. And the problem reads negative parentheses 4x to the 5th, y to the 0th raised to the 10th power. Okay, the first thing I would tell you to do is really, it's going to be helpful if you simplify inside the parentheses first, right? When you do this, I really want you to think about PEMDAS. I want you to think of the order of operations. That's going to be really, really helpful. So if you think about what's inside the parentheses first, you'll note that this 4 is being raised to the 1st power, the x is being raised to the 5th power, and the y is being raised to the 0th power. So in which case, isn't y to the 0 the same as 1? So if you had 4 to the 1st, x to the 5th times 1, wouldn't that still be 4 to the first x to the fifth? Yes, it would be. So now let's rewrite this. So we have negative 4 to the first x to the fifth, and all of this raised to the 10th power. Notice all I did was I rewrote the problem, but I took care of y to the 0th, which is simply 1. So I took care of that. Okay, I have a 10 on the outside of my parentheses, so I'm going to distribute, which means I'm using the power rule. So I use the 0 exponent rule, and now I'm using the power rule. Notice the negative is in front of the set of parentheses, so the negative is going to stay. I'm now going to distribute power times power. So this becomes 4 to the 1 times 10, which is 10, and then x to the 5 times 10, which is 50. If you want, you could punch in 4 to the 10th power just so we can see it. Notice it becomes 1,048,576, so it's still pretty big. I think I'm just going to leave it in exponential form. Awesome. Let's turn the page and try more problems. Okay, for number 2, we have 9m to the 8th n to the 0th power all over 3m to the 2nd n. This entire quantity is being raised to the 3rd power. What I would like you to do for this problem is I would love you to use the quotient rule, and then I want you to use the and you may find that when you use the quotient rule, you use another rule as well. I'm also going to say 0 exponent rule. And then I want you to apply the power rule. Okay, I'm just going to give you a couple minutes. When you have your answer, go ahead and throw that into the chat. Couple minutes starting now. So we have 9 and 3 as our numerical bases. Thank you, Ria. So because we have a 9 divided by 3, we want to simplify this first. So 9 divided by 3 is simply 3 with a 3 in the numerator. Again, if it helps, if you simply write 9 over 3, you're going to say, oh, that reduces to 3 over 1, right? Because you divide both by 3. So we have 3 over 1. Next, you have m to the 8th over m to the 2nd. Well, according to the quotient rule, you're going to keep the base and subtract the powers. 8 minus 2 is 6, but it's heavier up top, so you're going to be left with m to the 6th in the numerator. Notice we have n to the 0th power. N to the 0th power is simply 1. When you take that 1 and you multiply it by 3m to the 6th, it's still just 3m to the 6th. So I'm actually going to get out of the habit of writing times 1 because I know what that's going to result in. And then notice that because I took this n to the 0 and I made it a 1, I still have an n to the first in the denominator, right? So now let's notice this 3 is being raised to the first power, m is being raised to the 6th, 1 is being raised to the first power, n is being raised to the first power. So I've applied the quotient rule and the 0 exponent rule since both of those were inside the set of parentheses. PEMDAS, P in PEMDAS. This entire thing, this entire expression is being raised to the 3rd power. So now I'm going to apply the power rule. Power times power. Take this power and let's distribute. Your base is 3. Your power is 1 times 3, which is 3. Your base is m. Keep the base. 6 times 3, 18. Your base is 1, right? We keep the base. 1 times 3 is 3. And then your base is n. Keep the base. 1 times 3 is 3. And then we simplify. We know that we can do 3 to the 3rd. 3 to the 3rd, 3 times 3 times 3 is 27. So we have 27m to the 18th over, and then 1 to the 3rd is 1 times 1 times 1, which is 1, n to the 3rd power. If you had 27m to the 18th over n to the 3rd, that's perfect. You don't need the 1 in front. If you have the 1 in front, that's totally cool too, okay? And that's how you apply each of these rules. I honestly, truly believe that if you just keep practicing, have the index cards, exponent rule, or excuse me, let's try that again. Product rule, write down what you do. Keep the base at the powers. Quotient rule, keep the base, subtract the powers, leave it where it's heaviest. Zero exponent rule, anytime a base is raised to the 0th power, it's equal to 1. Power rule, keep the base, multiply power times power, right? And if you want, write an example. Keep practicing. This is going to become very easy the more you practice, and I highly recommend doing that. We still have one more rule. Let's check it out. Next, we have the negative exponent rule. So, as I do this, it's going to feel like I'm just doing a magic trick. It is founded in math, of course, right? It's a theory. We have x to the negative m. We know how to rewrite that. I just want to show you the best way to approach these so that it's very easy for you moving forward. So I want you all, as you're watching this, to follow the exact steps that I am taking, okay? So I'm going to go nice and slow to make sure that you're doing exactly as I am doing. That way, when we meet in Zoom and we discuss, these problems and we do some of them together, when you talk through the process, you should be using the same methods that I am using. Let's look. Okay. When you have a base raised to the negative power, notice that right now this x to the negative m is actually in the numerator. If it weren't, it would be written under a 1. So because you don't see the fraction, you know that it's in the numerator. So what ends up happening is you take the base to the negative power, you circle it, and you say, okay, well, I am in the numerator, so I'm going to move it to the denominator. And when I move it to the denominator, that act changes the exponent from negative to positive. Similarly, if I have 1 over x to the negative m, circle the base with the negative power, it is currently in the denominator, but I want a positive exponent. So I'm going to apply the negative exponent rule, which means I'm going to move it to the numerator, and then I'm going to change the power from negative to positive. So here are the steps. Circle the base and its a negative exponent. Move the base from the numerator to denominator or from the denominator to the numerator. Again, it depends on its location. And then simply change the power from negative to positive. You should never leave your answer with negative exponents. That is a big no-no, all right? We are not going to leave our expressions with negative exponents. We're always going to fix that. Let's take a look at part A. I'm going to show you a bunch of examples. We have negative 2 over y to the power negative 5, right? So, circle the base and its a negative exponent. Okay, my base with a negative power is y to the negative 5th. Even though I have a negative in front of the fraction, that negative right here, that's not a power. It's just a negative fraction. It's not a power. This y to the negative 5th, we notice, is in the denominator. So all I have to do is say, let's bring this to the numerator. As it stands, I already have a negative 2 in the numerator. So now I'm going to bring the y to the negative 5th up. And when I move that base with a negative power to the numerator, that power goes from negative to positive, and I'm done. I simply move the base of the negative power to either the numerator or denominator, wherever it is not located. You move it to that designated spot, and you change the power from negative to positive. Let's try that again. Take a look at B. Notice here we have negative 3 to the negative 2 power, x to the 4th power, y to the negative 8th power. Okay, we are going to circle the base and its negative exponent. This 3, not negative 3, this 3 is being raised to the negative 2nd power. This y is being raised to the negative 8th power. So the first thing I do is I circle both of those. They are both currently in the numerator. So I want to move these both to the denominator. So having said that, I need a fraction bar. in the numerator, I have a negative x to the fourth. And in the denominator, I now have 3 to the positive second power and y to the positive eighth power. You will probably note that we are not quite done because I do know what 3 to the second power is. So my final answer should be negative x to the fourth over 3 squared, which is 9. 3 times 3 is 9, y to the eighth power. That is your final answer. Let's do part C. Part C reads 4 to the negative 1, m to the negative 3, all over 4 to the negative 3, m to the ninth power. Step number 1, circle the base and its negative exponent. So we're going to circle 4 to the negative 1, and we're going to note that this will move to the denominator. We're going to circle m to the negative 3, and we're going to note this one moves to the denominator. I'm going to circle 4 to the negative 3, and I'm going to note that this one moves up to the numerator. So there's a lot of shifting going on here, right? There's a lot of movement going on. So let's organize what just happened. The 4 to the negative 1 moves down, so it becomes 4 to the positive 1. This m to the negative 3 moves down, so it becomes m to the positive 3. This 4 to the negative 3 moves up, so it becomes 4 to the positive 3. And this m to the ninth, well, it didn't move, so we leave it in the denominator. I hope that makes sense. You don't want to move a base if it doesn't have a negative power. You can't apply the negative exponent rule because it doesn't have a negative exponent. So keep in mind, you can't just move things willy-nilly. If you have a negative exponent, that's when you say base with the negative exponent, let's move that, right? And the act of moving that changes the power from negative to positive, right? Even if it's in the denominator, you move it up and it changes from negative to positive. That m to the ninth didn't have a negative exponent. It was m to the positive ninth power. So we keep it exactly where it is. Don't touch it. Let's see what happens now. So notice here I have a 4 to the third over 4 to the first power. Well, what that means is I'm going to actually apply the quotient rule. The quotient rule states you keep the base, subtract the powers. So if I have 3 factors of 4 and 1 factor of 4 in the denominator, when I subtract, I'm going to be left with 2 factors of 4 in the numerator because it's heavier up top, right? So that takes care of these. In the denominator, I have m to the third times m to the ninth. M to the third times m to the ninth implies the product rule. M to the third times m to the ninth, you're going to keep the base, add the powers. So it's m to the 3 plus 9, which is 12. That is very different from this expression. If you have m to the third to the ninth, that's very different from m to the third times m to the ninth. For this one, we'd actually apply the power rule. 9 times 3 is 27, power times power. But here, it's just m to the third times m to the ninth, so you keep the base and you add the powers. I hope that distinction is helpful to you. Part D, notice we have 2 to the negative fourth, x to the negative third, y to the negative second. What do you know? They all are going to move to the denominator, right? They're all in the numerator. So they are all going to move to the denominator. So it becomes 2 to the positive fourth, x to the positive 3, y to the positive second. But if they all go to the denominator, what in the heck do we write in the numerator? Well, I'm hopeful you all said that you need a placeholder, and that placeholder will always be 1. It's never going to be 0. If it's a 0, then the whole expression is equal to 0. So that doesn't make any sense, right? We move that to the denominator, which means our placeholder is 1. So our final answer is going to be 1 over, and then 2 to the fourth we can do. 2 to the fourth power right here is going to give us 16. 2 times 2 times 2 times 2. So we have 16 x to the third, y to the second power. All of that in our denominator, So there is our final answer. Beautiful. Let's turn the page. Your turn. What we're going to do for number 1 is we are going to simplify. We're not going to leave any negative exponents. But what we're going to do is we're also going to identify the exponent rules used. So for each of these problems, 1, 2, and 3, I want you to say, okay, I use this rule, this rule, this rule, and then here's the answer, right? I want you to go baby steps. What's the first thing I should use? What's the second thing? Then what's the third? And actually, just to make sure we're all on the same page, I'm going to do 1 with you, and then I want you to do 2 and 3 on your own. Let's take a look. So I have 5 to the negative second power, m to the fourth, n to the first, all over m to the negative eighth power, n to the second. The first thing I'm going to do is I'm going to use the negative exponent rule. That's the first thing I'm going to do. So I'm going to note that my 5 is being raised to the negative second power, and I'm going to move that to the denominator. And I'm going to note that my m to the negative eighth will move to the numerator. So that gives me m to the fourth, m to the eighth, right, because it moved to the numerator, n to the first, all over. We're going to bring the 5 to the negative 2 down to the denominator, so it becomes 5 squared. And we still have an n squared in the denominator. Notice how I'm taking this example and I'm breaking it down step by step. Small steps. Okay. The next thing I'm going to do is I'm going to notice that these two are being multiplied, m to the fourth times m to the eighth. That means I'm going to use the product rule. M to the fourth times m to the eighth, well, that becomes m to the 4 plus 8, which is 12. Also notice I have n to the first over n to the second, which implies I'm going to now use the quotient rule. So if I have n to the first and in the numerator and n to the second in the denominator, well, when I subtract, I'm going to have n to the first in the denominator. I also have 5 squared in the denominator, but I'm not going to leave it 5 squared. 5 times 5 is 25, and that completes my problem. I notice I use the negative exponent rule, I use the product rule, and I use the quotient rule in order to come to my final answer, which is m to the 12th over 25n to the first. Okay, go ahead and try problems 2 and 3. Number 2 reads negative 18, a to the fourth, b to the fifth, all over 6, a to the negative first, b to the 0th, raised to the second power. And then number 3 reads 6, a to the negative fourth, b to the third, all raised to the negative second power. I'm going to give you a few minutes. Let's do 4 minutes, and then we're going to check in. Okay, 4 minutes starting now. Okay, first things first for number 2. We want to simplify what's inside the set of parentheses first. And I'm actually going to begin with the negative 18 over 6. If it helps, if I write negative 18 over 6, you would reduce that all day long. You would say, well, negative 18 over 6 or negative 18 divided by 6 is simply a negative 3. So I'm going to rewrite this, that this becomes a negative 3. Next, I'm going to notice that a to the negative first power means it's going to move to the numerator as a positive power. So that becomes a to the first power up top. And then notice that b to the 0th power is simply 1, and 1 times anything is anything, so we're not actually impacted by that 1. So now I'm going to rewrite this because it's a little messy. So I have negative 3, a to the 4th times a to the 1st times b to the 5th, all raised to the 2nd power. Well, I want to combine these first. So I use the negative exponent rule. And I actually only use the 0 exponent rule. Okay, that's actually what I did. I did not use a quotient rule because I didn't have to. Next, I'm going to multiply these two, so I get negative 3a to the 5th power, b to the 5th power, raised to the 2nd. So I've just used the product rule. Okay. At this point, I notice that each of my bases is being raised to a power. This is 3 to the 1st, a to the 5th, b to the 5th. I'm then going to distribute that 2. Notice the negative is inside the set of parentheses, so when you square a negative, it becomes positive. My answer is positive, so now let's keep the base, multiply the powers. Keep the base, multiply the powers. Keep the base, multiply the powers. And you're almost done. 3 squared is 3 times 3, which is 9. So your final answer is 9a to the 10th, b to the 10th. And the final rule was the power rule. All right, I know I kept you 2 minutes longer, but I hope that made sense. What we'll do for tomorrow's class is we'll take a look at 3. Try this on your own. Do 3 right now while you're sitting here. Knock it out, see if it makes sense, and I'll tell you how well you did tomorrow. Also, take a sneak peek at identifying the missing exponents in the 2 problems on the same page. Take a sneak peek. Let's see what you think about that tomorrow. Excellent work today as always, and I will see you all tomorrow. Don't forget to vote. Bye, everyone.